finish this topic. The major thing is that we're talking about PID controller. So there are two things you guys need to understand. One is okay. Physically, if we're talking about motor, let's say you guys are using a remote car, a toy RC car. So you put battery. In the system, 9 volt. Right? This is pretty 4.5, right? 4.5 volt. So your car is moving and rotating. Now all of a sudden, you say, okay, speed is too slow, and you just change your knob, saying that the output is like you want to have the speed to be increased. When you have a motor, you want to increase the speed of the motor. What you need to do? Increase what? Current or voltage?
Voltage.
Okay, so can you go over 4.5 volt? Can you? Of course, if you say you want to change this one, then you can. But if this one is fixed, then the maximum output is 4.5, unfortunately. So if you say this one is, KP is 1,000, what is the maximum error you can have? 4.5 divided by 1,000, which means the KP has its own limitation. You can do anything you want to if you are designing everything using MATLAB, because it doesn't matter what you do. MATLAB is just going to implement the number. But if you put everything in your controller in physical setup, your voltage got its maximum. Output of controller must be smaller or equal to the maximum voltage you can generate. Does it make sense? So when you are dealing with something like this, KP must be smaller than a certain amount of number, depending on how much error you have. Sometimes your error is just a little bit, maybe 0.01, 0.02, then you can use high hand, then everything is still stable. But if you have everything, if you multiply this number by this number and it's greater than 4.5, your system is going to be saturated. Just, I think you guys learned this in 电路学. Okay, you have sine wave. Output. So after an amplifier, the output becomes 0 to 9 volts. But your power supply tells you you can only generate positive minus 4.5 volts. What happened? Everything is going to be truncated. I think you use click when you are learning electronics. This one over here, we call it saturation. Okay, so anything greater than this number, you cannot implement. You can only implement 4.5 volts. That's the limit. So over here, you got 3 numbers. This one over here, you know you cannot have any number of KP you want to have. You need to know what is your what is the range of your error, then you design this KB accordingly. The other thing, this one is going to be a little bit difficult because it's integration from 0 to infinite. So even though your Ki is small, chances that this is going to have saturation when it's reached a certain amount of time. This thing is wind up. And if you do differentiation or decontroller, when you are, keep in mind when you are using microprocessor or using MATLAB, you cannot actually do differentiation. What we're going to do is KD delta T delta error, right? We cannot do differentiation. We can only do delta over delta. So if you are having something like this, if your delta, let's say this is, we say it's going to be 100 Hertz, this number, the difference is going to be divided by 0.01. If you say it's going to be 1 megahertz, this is going to be this number. So if this one is just a little bit, you're going to multiply that by 1 million. So it can be saturated easily. So when you are dealing with your PID controller, this one is going to wind up. This one is going to saturate your system. This one is going to be too much if your KB is too huge. So all those kind of things, you will need to do something we call anti-wind up or other method to deal with those kind of things. The easiest way of doing this thing is after a certain amount of time, I just reset this integrator to be 0, which I don't really like that. But it is possible that after a certain amount of time, your error becomes 0, so you can reset everything without affect your system badly. There are many ways of doing those kind of things in your textbook. Franklin talk about those kind of things. The textbook written by Franklin talk about a lot of those kind of stuff. You might take a look at those parts. Then those are more like implementation. When you have a real system, how are you going to take care of those kind of things? Those part, I'm not going to put that in the test. I just need you guys to understand there are such kind of phenomena that is going to be existing in your system. This part is actually nonlinear. Okay, we are not going to touch anything nonlinear as undergraduate students. So you guys are okay for this part. If you really want to know about nonlinear system, go to graduate school. Okay, next thing we're going to talk about is stability. The first thing I want to ask you guys is, what is a stable pole? You guys answered me a few minutes ago. What is a stable pole? Right? That is something we learned so far. Because if your pole is positive, it means that you're going to have divergent response. It doesn't matter you are having an impulse input, or you have a step input. When you have pole located on the right hand side, your system is unstable. So stability is based on that. So what's the big deal? There are a few things, because we are having a system which the order is way higher than 2. So when you have like 4th order, 5th order, or 10th order, how are you going to determine the stability? You can tell me. I just use MATLAB, right? However, MATLAB costs $100,000 if you goes to industry. Believe me, your boss won't buy that for you. If you get that from some place illegal, it's your responsibility, not his responsibility. Okay, so do not do that. So we have other ways to determine stability. That is something we're going to talk about. But there is one specific term over here. It says the system is called asymptotically stable. And the impulse response case to, what does that mean? I got a system. I got the input. I got an output. So I'm telling you, the definition is asymptotically stable. Means that on this side, let me give you one example. You use a hammer to hit this cantilever. What happened? It's an impulse because I only apply a certain amount of force to the system at time equals to 0. Then I don't apply any force to that. That is called impulse input. So when you are having something like this, what are you going to expect? It's going to vibrate. And this is something you're going to expect, right? And does this one decay to 0? Impulse, this is the impulse. Does this one decay to 0? Yes. So this one is called asymptotically stable. This is definition, and you're going to see this term many times in your textbook. So just be sure you understand what is this stable means. When you have something like this, your input is impulse. So it's going to be like this. 0. This is delta t. Y. U. Okay. You can look into your engineering mathematics textbook. They have direct delta. They have delta. They have different definitions. If it's continuous or this one is discrete, it might be KT, it might be 0. They have different kind of definition. Just look into the definition, you know what is your impulse input, and what is delta T, okay? And the output over here, if it's a second order system, it's going to be like this. If it's a first order system, it's going to be like this. It doesn't matter. You have your system like this, or you have a system like this, or you have your system like this. As long as it decays to 0 with certain amount of slope, we call this one asymptotically stable. Okay? Why is that important? So if you are having something asymptotically stable, when you have step input, you are going to see something like this. If it's a first order system, it's going to be like this. So your approach to a steady state within infinite time. So that is something we call asymptotically stable. Okay. Observation. So let's talk about stability. In physical system. Here's one. Okay, so have you guys taken vibration? The course of vibration?
No.
No? Do you guys need to?
No.
Okay. So what happened to this one? You guys learned dynamics already, right?
Yes.
So when this one is on the highest point, what happened? The speed becomes 0. So you got kinetic energy equals to mgh. When this one is swinging, it will go to the lowest point over here. And over here, this will achieve to its highest velocity and 0 potential energy. At that time, the kinetic energy becomes 1/2 mv squared. So based on conservation of energy, this one is going to go into this one, and this one is going back periodically. So if I don't have any component over here that is going to consume any energy, what happens? Will this pendulum stop swinging?
No.
It will be like this forever. So when you are doing something like this, without damping, is this one stable?
No.
Yes or no? You guys still remember the S domain thing? When this one is swinging like this, is that going to be a sine wave or cosine wave or anything like that? Yes, it will be. So when it's doing something like this, will that magnitude going to be reduced since I don't have any damping? So where are we going to have our pole? Along the imaginary line. When you are doing those kind of things, be sure you connect everything into physical system with the S domain. In this case, since this one is moving back and forth, the magnitude is not going to be changed, which means this one, whether is this one stable, or is there any specific term we're going to call this thing?
Critical.
Right. This one is critically stable because it's swinging back and forth all the time. So it's going to have something over here. Okay, so in this case, we still call it stable. Question, is this one asymptotically stable?
No.
No, because if you impulse, it's like stay over here, and you just touch that one force using a delta function that's horizontally, then what happened? It will swing forever and never stop. So definitely it doesn't fulfill the definition asymptotically stable. Case 2. Pendulum with anchor. In this case, if you, of course, the stable point is going to be theta equals to 0 degree, right? So if you have things over here, then you put the impulse response to this one. What happened? Since I have a damper over here, what happened? I'll have, right? I add a damping to a system, which means I add a pole to the left-hand side. So when I do something like this, it can be a first order system. When this one is a first order system, this one becomes stable or not stable? Stable, right? So this one is stable. What kind of stable? Is that critically stable or asymptotically stable?
Asymptotic.
Right. So this is going to be asymptotically stable. For some reason, I think the 硕士班数学卡 like to have this term included. It doesn't really make sense to me, but anyway. Third one. Inverted pendulum. So if you do everything carefully, you should be able to do something like this, right? Right? You just put a ball over here and put a ball on top of it. Nicely. Now, you know who will come here. So the girl put a slightly force to this one. What happened? Well, this one certainly is going to be 0 degree. So when I put a small force to this one, which is impulse response, will this system return to 0 degree? No. No. So is this one going to be stable?
No.
No. So inverted pendulum is going to be unstable. This one is going to be only stable when it's over here. Right? So this one is critically stable. This one is asymptotically stable. This one at this position, that is unstable. Is that clear? Everybody understand how we define physically stable, unstable, and critically stable? Should be pretty straightforward to understand, right? So if we put everything into transfer function, certainly, if we do certain fractional decomposition of this transfer function, we might get something like this. So if we do inverse Laplace transform, what are we going to have? We're going to have A exponential AT plus B exponential BT. Clearly, since I don't have negative sign in an exponential term. This one is going to be divergent. This one is going to be divergent, which means those two can never converge to 0 when I have impulse input, which means the system like this with positive poles, they are going to be unstable. For second order system, it's going to be the same. G of S equals to K S minus rho plus J omega S plus rho minus J omega. So if you do the inverse Laplace transform, you're going to find out if U of S equals to 1. This one over here, Y of S is going to be K omega 1 by omega S minus A rho square plus omega square. Okay, this is something I believe you guys can do that at home. So if you do inverse Laplace transform, you get K over omega exponential rho t sine omega t. So what happened is unstable, since you have this part which is increasing exponentially divergent. So the overall system becomes unstable, which means mathematically, if you have everything that is going to have positive poles, your system becomes unstable. Okay. Since I know my system is going to be unstable when I have poles in the positive or right hand side of S domain. So what? What am I going to detect those kind of things? Is there any way that help us to detect those kind of things easily? Yes, we do. We have one thing called roots. So if I have a polynomial, which is not second order, because second order is, you can easily come up with the roots using quadratic equation. Minus, if you have a x squared plus bs plus c, you can always find out what the two roots of this thing, right? But if you have like fourth order or higher order, can you get something like this easily? No, unless you have MATLAB or you have Excel. Otherwise, it's very unlikely you can get the roots directly. So when we are having something like this, keep in mind, I'm dealing with transfer function, output over input. So you might have something like okay? Most of the time, when you are dealing with your system, after you take in how to model a system altogether, if you take Doctrine's system modeling, this is going to be the equation you're going to have. Even though what we desire is to have if you can have this form, then everything is easy. You can just determine whether PI is going to be positive or negative. But the reality is you can only have something like this. So when we are dealing with something like this, we need to determine whether the system is stable based on this representation, okay? So when we have this representation, tell me which part is important to us, the denominator or the numerator? Denominator, because we talk about the poles, the zeros over here might not be important to us. It might give us some kind of a positive sign or negative sign, but it won't determine whether the system is stable or not stable. So when we are dealing with those kind of things, we are always interested in the polynomial of the denominator. Okay? And there is a way that we're going to deal with this kind of things easily. That is something we call Rules-Hurwitz stability. So, first thing, we're going to do that with two rows. So, we're going to have the coefficient over here is 1. Put it over here. The coefficient for the second one is A1. Put it here. Third one is not going to be moved down, it's going to move to this row until you got A3, A4, and A5 until you finish all the AN. If you have your AN over here, this part over here just fill that with 0. If you have your AN minus 1 over here, then you have AN over here. Okay? If you don't have anything over here, just put that as 0. The worst scenario is you're going to put 1 0 over here. Make sense? Well, it won't make sense to you, but that's just a rule. Okay? So, what are we going to do? We are going to do something like this. A1, A2, minus 1, multiplied by A3, divided by A1. This one multiplied by this one, minus this one multiplied by this one, divided by this one. Is that clear? Of course not. This is just a formula. This is a formula that you can, you're going to find out in your notes. Just remember that. So the first column over here is going to be this one multiplied by this one, minus this one multiplied by this one, and divided by this one. The second component over here is going to be this one. This one over here is going to be this one multiplied by this one, minus this one, divided by A1. Then the third one is going to be similar until you finish up all the components over here. Then you get a lot of things over here. Okay, then that becomes this row. Then C1. Then you start to do this one. Then you do this one multiplied by this one minus this one multiplied by this one and divided by this one. Then you put it here. Then keep on going until you have only one component over here. Okay? I know it doesn't make sense. But do you understand what I'm talking about?
No.
You break my heart. But this is just a formula. You just follow the formula. You don't. This is criterion, which means some people crazy in Russia create a formula which is crazy. I don't understand why is that, but people use that all the time. How many of you are going to do the master entrance exam in the future? 硕士班考试. This one is going to be hot and very popular problem. It doesn't matter you like it or you don't like it. Just remember that. 记起来就对了. There is nothing I can do. Okay, this is just a formula. Okay, nothing really specific. Now, you got all the components over here. Now this is going to be critical part. You need to, so the first one is 1, the second one is A1. So those two are positive numbers. If you see any changes sign in the first row, it means your system is not stable. If you see everything is the same sign, it means that your system is stable. That's how we determine whether it's stable or not. Is there anything to prove that? I believe so. But do you want me to prove that? I believe you don't want to see me doing that. I will put you guys to sleep in 5 minutes. So I don't think it's a good idea. It's just a formula. Example. So I want to do so if my AS equals to this one, I want to determine whether this system is stable or not stable. There are two, again, you have many ways to do this. You can use MATLAB. So it will give you all the roots. If you see anything positive, it means that your system is it means your system is not stable. Make sense? That's the easiest way. However, when you are taking the test, you cannot do that. You need to use those rules. So we got fourth order, third order, second order, first order, zeroth order. We just need to fill the first two rows from 1, 2, 3, 4, 5. I don't have anything over here, so which number should I put over here?
0.
Okay. First number. This one multiplied by this one, minus this one multiplied by this one, divided by this one. 1? Good, thank you. So this one becomes 1. Okay, it's just a formula. Does that make sense to me? No. But you just need to remember that. Second one is going to be multiplied by. Okay? Any questions? Okay. So I'm going to erase this one because it's going to be ugly. I'll just put 1 and 5 over here. So this one over here is going to be 4 minus 10 divided by 1. By now, you should be able to tell whether the system is stable or unstable, right? Because it changes sign, so it's unstable. The second one over here is going to be 5. So this one over here is going to be 0. So you don't need to worry about this one at this moment, but this one over here is negative 30 minus 0 divided by minus 6. So I got what? 5. How many times I change my sign? 2 times. So it's stable or unstable? Unstable. Any question? Is that clear? Everybody understand what I'm talking about? This one is going to be popular in my test and in many other tests. If you are going to do PhD in the future, this one in many it will be in the problem in many universities. Of course, it's not that easy. Any question? If not, that's for today.